Welcome back, and today's video is about implicit differentiation. So this features in almost every single calculus course that you'll be doing at college or high school. It's all to do with a relation between x and y. So if you have a quick look at this expression here, we cannot make y the subject of the expression, therefore making y a function of x almost impossible in most cases. This is known as an implicit relation, and in order to differentiate that and find the gradient at a given point, which requires a few steps. Let's dive in. Okay, so after a brief introduction about what implicit differentiation is and how we do it, I'll run through a series of questions in this order. If there's one particular letter that you want to have a go at, jump ahead in the chapters. Otherwise, take a photo, have a go at them yourself, and work through them with me. Okay, so just before we start, I think it's important to get our heads around what is actually going on with these implicit relationships. So have a quick look at this circle on the left here. If I drew a vertical line through this, it will fail the vertical line test. Therefore, it is not a function. Therefore, it is an implicit relationship. So in this case, x squared plus y squared is equal to 1. So this is the equation for a unit circle. So if you go ahead and you find a value or take a value of x, you'll be able to find a corresponding value of y. But it fails the vertical line test because there is a second value of y that it could be. So if you took the same value of x, it could end up in this other value of y. So we need to know when we're doing these questions, possibly the x and y value that we need to substitute in to the result of the gradient in order to find the correct gradient. So if you draw a tangent here, we can see that clearly has a positive gradient. But if you go up to this one and draw a tangent on this part of the circle, it has a negative gradient. So it really depends on where we are on that circle, on that implicit relation, what the value of the gradient will be. When we differentiate this with respect to x, we would simply get 2x, okay, using the power rule. But when we differentiate this value with respect to x, we don't know how y is changing, okay, as x changes. So what we'll do is we'll do what we did when we did chain rule. We'll say that the change of some value, in this case y squared, with respect to y, then multiplied by dy by dx, would actually be the derivative of that. And so what we can do is we can differentiate y with respect to y. In this case, you would get 2y, but then we'd need to multiply it by dy by dx. Now, we don't know what dy by dx is because we don't know what the rate of change of y is as x changes, but that is an important step. So that bit there is to do with chain rule. And just bear that in mind because we'll use that in every single part of the next few problems. So also we would need to differentiate 1 with respect to x, and when we would differentiate a constant with respect to x, we would just get 0 because there are no x's involved here. Okay, so part A is a relatively simple expression. So it's asking us to differentiate with respect to x. So we have d of, and we have y to the minus 1 by dy times by dy dx. Now that was that part of chain rule that I stated, but we could actually find this value. So when we differentiate that with respect to y, we would get negative 1 y to the minus 2, but we don't know what dy by dx is, so we have finished that result. You can simplify that up by just writing negative 1 over y squared dy by dx, but there's not much more we can do with that, okay, unless we were given some more information. Okay, so part B says find the gradient of the tangent to this expression at point 2, right? So at point 2. So I've drawn this on the calculator. If your calculator has the ability to change the input from function to relation, you'll need to do that, as you will not be able to enter it as a function. You have to enter it like this. Okay, and that is the shape it gets. Now, I've just drawn the graph because it says find the point at 2. So I just kind of want you to visualize where that point is. Let's say that's 2 here. Then the gradient of that curve will be something like that. Right, now that will just sort of help visualize what's going on in this question. So let's have a look at how we differentiate this. Well, we want to differentiate both sides with respect to x. So we're differentiating the left-hand side with respect to x. So we're differentiating all of this with respect to x. But we also need to differentiate the right-hand side with respect to x. Okay, so that would be step 1. When we do that, we would get 2x plus, now we're going to differentiate y first, which is 3y squared, and then have to multiply it by dy by dx. So if the whole chain rule thing is confusing you, just differentiate y first using the power rule, then times it by dy by dx. And that is equal to 0, okay, because the derivative of 5 using the power rule would yield 0. Therefore, then that would leave us with 3y squared dy dx is equal to negative 2x. And in this case, you want to get dy by dx on its own because we want to maybe find the gradient at a certain point. So therefore then dy by dx is equal to minus 2x over 3y squared. Now this is looking very good because we have an expression now for gradient. But the thing is that they only gave us the value of x is equal to 2. And in order to solve this, we would need to sub in a value for y also. So we need to go ahead and find that value of y. So what we'll do is we'll use that 2 that they gave us and we'll plug it in to the original function, which is x squared plus y cubed is equal to 5. Now I'll just do this up over here. So if 2 squared plus y cubed is equal to 5, then y cubed is equal to 1, and therefore y is the cube root of 1, which is 1. So therefore the value over here is actually 2, 1. Now that's very important because we need both of those values to plug into this. So 2, 1, so we go down here. So now I'm going to substitute in that the y is equal to 1. Right, so let's plug all of that in. So we get negative 2 times 2 is minus 4 over 3 times 1 squared, which is 3, which is minus 4 over 3. Part C here. So it's asking us to do the same again, differentiate it, and then also they've told us y this time. Differentiating x, so we will get 1, but now we have to differentiate the y. But then also do not forget the dy by dx. That is super important because we'll need to make that the subject. The other side of the equation, is equal to 4y. So differentiating that, we will just get 4. That's the derivative of y times by dy dx again. So every time you're differentiating y, you have to differentiate it and then times it by dy by dx. I want to make dy by dx the subject. So I'm going to move this to the left-hand side. I'm going to move the 1 to the right. So basically minusing 1 on both sides and minusing 4 dy dx on both sides. So therefore that gives us 3y squared dy dx minus 4 dy dx is equal to negative 1. Now I'm going to take out a factor of dy by dx on both these expressions. So dy dx, open brackets, 3y squared minus 4, close brackets, is equal to minus 1. You can just simply divide both sides by 3y squared minus 4 now. So dy dx is equal to negative 1 over 3y squared minus 4. Now, in the previous example, I had to go ahead and find the x value if they only gave us one of these values. But in this one, it doesn't look like I need to do that because there is no sort of x term in this final result. So that's fine. I could just go ahead and substitute, was it 1 into this? So therefore, substituting 1 in would give us negative 1 over 3 times, so it'll be minus 1 is equal to 1. So the gradient at that point is 1. Okay, D. We have an expression here, but this one involves product rule. So also that's going to be 3y squared times dy dx plus, now this is where things get a little bit tricky. We've got to separate this up. Okay, because it is still a product of two values. So it's u, v. Now, our product rule was v times du plus u times dv. So what we have to do now is let's just think about that. We've got v is y squared. Du is the derivative of 3x, which is just 3, plus u, which is 3x times the derivative of v. Now, this is the one you have to be really careful of. So as we saw in the previous ones, it was 2y. Take 1 off the power, just makes it to the power 1. But then times dy dx. Right, so that is that little part. Now we've got to do this over again. With this part, we have minus. Now we have another product here. So we have u and v. So we'll just do exactly, I'll just bring this over so you can see how I'm doing this. There. And remember, it's minus all of this. So everything's got to go in a bracket here. So we have v, which is y. The derivative of u, which is just 1, plus u, which is x, times the derivative of v. Now, when you differentiate y, you just get 1, but then you still got to times by the dy by dx. So there are many places there you could just forget something, so please don't. Just double check your answer. And that is equal to the right-hand side. When you differentiate 0, you're just going to get 0. Right, so we have to tidy this whole thing up now. So we're going to take out the dy by dx. So we have dy by dx. So I'm just going to take it out of there. I'm going to start factorizing this up. So we've got 3y squared. Now, there is no dy by dx in this term, so that is going to go to the right-hand side of the equal sign. So I might as well do that now. So that'll be minus 3y squared. But there is a dy by dx here, and that is 6xy. So we need to have a plus 6xy. And we have one more expression. Here we have minus y. That doesn't have a dy by dx in it, so that minus y moved to the right-hand side will become positive y, but we do have a negative x dy, so minus x. Divide everything through by this value on the left here, which is this one. That will give us minus 3y squared plus y all over 3y squared plus 6xy minus x. That's the end of that question. Okay, moving on to our last example. So it's another derivative of a product. So there's a product here and a product here. So we can call this one u and this one v. This is obviously a different u and a different v, but we'll need to use product rule. So let's go ahead and differentiate with respect to x. So we have v du, okay, plus u dv. And that's obviously by dx. And therefore then we would get, so v is e to the 3y, du dx is 3x squared. Now, I can just put that, I'll just put it here, 3x squared, plus u, which is x cubed, and dv. Now, the derivative of this here, so e to the 3y will remain as e to the 3y. But then you have to multiply through by the derivative of the power, and that would be 3. So I'll just put that at the beginning of this expression. But then we mustn't forget that we have the dy by dx as well, like we did on all the other examples, and that I'll factorize that out later. So let's move on to the second sort of expression here. And we've got v du plus u dv again. And let's go ahead and plug these values in. So we've got v, which is y cubed, du by dx, which is 8x, and then plus u, which is 4x squared, and dv by dx. Right, so again, we have to differentiate this using implicit differentiation. So we're going to get 3y squared, so this would be 3y squared, and then the dy by dx. So I'm just going to put that in pink so we can easily see when to factorize that out. That is equal to the derivative of the right-hand side. Now, that is all in terms of x. So we just differentiate an exponent like normal, and watch my video on that if you haven't already seen that. So this would remain exactly the same, and then we times by the derivative of the power, which is going to be negative 2. So this whole expression on the right here will end up being minus 54e to the minus 2x. Okay, so that's that dealt with. Now let's factorize out these dy's. So I'm going to take out this dy out of both of these expressions and put dy by dx here. Then I'm just going to put open brackets, and inside that then I'll have this first of all. So we've got 3x cubed e to the 3y. So that's, I'm just going to cross it off so you can see that I've dealt with it. And then I now have this expression plus 4x squared, then 3y squared, close brackets, so that's that dealt with. Now, the other expressions that I'll just underline here with a squiggly line, and this one need to go to the right-hand side, so I'm going to subtract them both on this side and move them over to the right. Okay, so therefore then we will have minus 54e to the minus 2x, subtract e, 3y, 3x squared, and then minus y cubed 8x. Right, so we need to now divide everything through by this term here. Right, so we need to divide everything through. dy by dx is equal to... Now, I'm just going to look for some factorization that can go on here. I can see that we could take out a factor of 3 on the denominator and an x squared. So we could have close brackets. Okay, so that would be factorizing the denominator. And then on the numerator, I don't think there's much I can do here with that. I don't think there's anything I can do, so I'll just copy that and just paste that on the numerator. And there we go. There is a slightly more complicated implicit differentiation. Without knowing any value for x and y, we can't substitute anything in, so we can't actually calculate the gradient at a given point, but that's easily likely in a question. Stay tuned for more exam questions using implicit differentiation. Don't forget to smash the like button, subscribe. I'll see you next time.